to chapter 16, I think. So we're going to talk about in this chapter thermodynamics, and um, you probably talked about some thermodynamics in Chem 50, and that had to do with energy, like delta H, right? Which is again our change in enthalpy. And remember that if we have a delta H, that is a negative value. Again, it is a exothermic process in terms of energy and heat. That means heat and energy is being released. If we have a delta H that is a positive value, then it's an endothermic process where heat and energy is being absorbed. Really, the first law of thermodynamics is the law of conservation of energy. So as you hopefully know, right, we don't create nor destroy energy, but it can be transformed from one place to the next. And when we think about energy, we think about it almost as a pure sort of transition, if you will. Like if somebody loses a certain amount of energy, somebody else there will gain a certain amount of energy. So the energy sort of component of thermodynamics you start talking about in Chem 50, again, where you did probably your enthalpy, your Hess's laws, your specific heat capacity probably as well in there as well as you did that. So here we're going to talk about the rest of sort of the thermodynamic properties. And we're going to talk about entropy, which is actually delta S. So some new letters, which is kind of nice. Free energy, which is delta G. And of course, we can't forget about our friend equilibrium, right? So we will tie that back in at the end of the chapter here. So let us talk about a couple of things here. And the first thing when we talk about sort of thermodynamics is a lot of times we refer to the idea of spontaneous type of reaction or process. And sometimes people have sort of the wrong idea in terms of what spontaneous sort of means in this context. So when we talk about spontaneous, and if a reaction, for example, is spontaneous, uh, it has really nothing to do with how fast or slow the reaction is taking place. So sometimes when people talk about spontaneousness or spontaneity, people think if the reaction is spontaneous, you snap your fingers and it's going to happen really, really fast. And that's not what we're talking about here. But what we're talking about is if a reaction is spontaneous, what that means is under those conditions, you would expect the reaction actually to occur without any sort of intervention to make it occur. If you just leave it there long enough, that reaction should actually occur. Now, that means that that reaction could occur really fast. It could also occur super slow, and it could occur anywhere in between. So what deals with, bless you, how fast or slow a reaction is what we talked about at the beginning of the semester, which is kinetics. So kinetics deals with the idea of how fast or slow a reaction. Here in thermodynamics, we're just really a lot of times trying to figure out, will this reaction take place, basically? And if it does, it's referred to as being spontaneous. And again, that has nothing to do with how fast or slow the reaction may take place. And if it does not occur, then that reaction is sometimes referred to as being non-spontaneous, which means under those conditions, it will just never happen, basically, unless you do something to it to make it happen. So sometimes books and people will maybe not talk about spontaneous and non-spontaneous. Sometimes they'll refer to it as, is it product favored or is it reactant favored? And that's kind of the same idea. If something's product favored, then that means that reaction is probably going to be spontaneous. It's going to head to the product side. And if something is sort of thermodynamically reactant favored, that means that probably is not going to happen. That reaction is going to kind of hang out there on the reactant side. So sometimes people refer to it in that sort of connotation. But here we're going to talk about spontaneous and non-spontaneous. And again, that is essentially what we're talking about. Will this reaction occur? Pretty much if you don't do anything to it, it will happen if it's spontaneous, and it will not happen, obviously, if it is non-spontaneous. Now, these are some examples of spontaneous physical and chemical processes. As we know, water, goes downhill, doesn't usually go uphill, right? Unless you help it out. So again, that's a non-spontaneous process, right? If you want to shoot the water uphill, maybe like a pump or something to do that. But it will just not go up by itself. Obviously, sugar will dissolve. Water freezes below 0 degrees, and above it's 0, it starts to melt. Heat does flow from hotter objects to colder objects. If you have a gas in a evacuated bulb and you kind of open it, it will sort of fill and expand. And iron, all you need is a little bit of moisture and some oxygen, and you're good to go for rust. It will occur sort of spontaneously. Obviously, if you're skiing here and you're starting at the top of the hill, that's a pretty spontaneous thing. You just need to kind of go over the hill, right? And then you're just going to go, right? This going back upwards the hill is a non-spontaneous process, right? You can't do that without putting in some type of work, right, to get yourself up there. I'm imagining this guy does not really want to see this guy coming up as he's coming down. That's probably not a good idea in this case. Up on top, again, is a spontaneous sort of process here. If we had gas molecules separated by a valve here and we open the valve, spontaneously, these gas molecules are going to basically fill the other side. It's just going to happen. Non-spontaneous would be if we had gas molecules on both sides and we wanted them all to end up over on one side. They are not going to just magically all kind of head in that direction without some help, right? Maybe you could heat it or something like that and convince it maybe to go that direction. But without some external type of help, it's not going to happen by itself that they're all going to go basically to the left there. So that brings up the idea of heat, which is the first law of thermodynamics, the conservation of energy, and the idea of whether or not if a reaction is exothermic, for example, does it help in terms of spontaneity? Now, when we look at this is methane, basically. This is like a Bunsen burner, right? And it's a negative reaction, and this is a spontaneous reaction. Here we have basically an acid-base reaction, making the formation of water, also a negative sort of process. But here we have this process here, which obviously is ice melting. And we know that is a spontaneous process, right? Because if you just take an ice cube out, it will start to melt as the heat will transfer from the surrounding air to the ice cube, which is colder, and it will start the melting process. And that is actually a positive value. That's the heat of fusion right there, 6.01 kilojoules per mole. And dissolving ammonium nitrate here in some water is actually an endothermic process. So what this shows us is delta H, or the change in enthalpy, is not really the ultimate factor in determining whether or not a reaction is spontaneous or not, as we have some that are negative and exothermic reactions. We also have some positive endothermic reactions that are spontaneous. You could have a spontaneous reaction, as you can see up here, that is exothermic or endothermic. You could also have non-spontaneous reactions that are exothermic and endothermic as well. But exothermicity does favor spontaneity. So there's two sort of things, as we'll talk about, that sort of helps with things becoming spontaneous. And one is sometimes referred to as like the spread of energy. So if something's exothermic, that's going to release some energy, kind of spread the energy out. So that does, in a lot of cases, sort of help things become spontaneous. And also the kind of spreading out of matter and stuff like that also sort of helps things become spontaneous as well. So just because it's exothermic, it doesn't necessarily mean always it's going to be spontaneous. It could be non-spontaneous. And just because it's endothermic, again, doesn't mean that it's always going to be non-spontaneous. It could also be spontaneous as well. So we need another sort of value to help us understand spontaneity. And one of those things that help us get to that idea of whether or not a reaction is spontaneous or not is entropy. And entropy is abbreviated with an S. Delta S is the change in entropy, not to be confused with obviously enthalpy, which is delta H, right? So that is enthalpy. Entropy is the amount of randomness or disorder there is in a system. And one of the unusual sort of things about entropy, in a sense, is actually when you have a lot more disorder, you actually have a more positive value for entropy. So entropy becomes more positive as the craziness, the disorder, that basically starts to increase. So as the disorder increases, you will see the change in entropy become more positive. Opposite of that is as the disorder decreases, or the order increases, whichever way you want to think about it. If you have a lot more ordered type of situation, the entropy value actually starts to decrease and the entropy will be more of a negative value. So if you have delta S that's more negative, you're getting a lot more order that's happening. If you see the delta S basically become positive or is positive, you're creating a lot more disorder and craziness. How do we calculate the change in entropy? One way that we could calculate it is pretty much how we calculate everything else. We could take our products minus our reactants. Remember that things like enthalpy, entropy, and stuff like that are state functions, and right, so state functions, basically the only two things that are important is where you start and where you end. So beginning and ending difference is really what we look at. And one of the easiest sort of ways to sort of visualize or sort of see entropy is actually when we do a change of state. So obviously in the solid state, things typically are packed in pretty ordered, right? They're pretty ordered with each other. And in the liquid state, things have a little bit more energy. So they're moving around a little bit more. So there's a little bit more craziness happening, right? Everybody's kind of moving around a little bit more. And then obviously when you get to the gas phase, there is a lot of craziness because this is like a lot of things just flying around, right? Moving around and stuff like that. So as we go from solid to liquid to gas, the amount of entropy or disorder starts to increase. So we get a big increase in the amount of entropy. So as we look at our sort of ice going to liquid water, that is going from a more ordered state to a more disordered state in the liquid state. And we would expect a delta S here to be more positive in this case, again, because we're increasing the amount of disorder that is happening in this case. Any questions on that there? Actually drew that picture perfect, like right between the two things. That was pretty good. All right. So when we talk about disorder, it is related to probability. And when we talk about probability, a probable event is one where there are multiple ways that something can occur. An improbable event is one where there are only a few ways that something could occur. So for example, if we were in this room and there was like 3 doors, right, all around, it is very probable that we all could get out pretty easily, right? You just pick whichever door you want to go out. It's a pretty good chance we will all get out of the room, right? Now, if we happen to be in this room and there was no doors, but just like a small little window in the top corner of the room, it's probably less probable that we will all get out there, right? Because you got to get up to the top and stuff like that. So, the more ways something can happen, the higher the probability that it will occur. And, if there's only kind of one way to do something, right? Sometimes people say, right, it's only one way to do something right, right? So there's less probable that you might do something right versus you might do something wrong. There's a lot of ways to screw things up, right? So there's a lot more ways that you can mess things up. So in an ordered state, to get something really, really ordered, it should have a low probability of occurring, and it would have a small entropy. And in a disordered state, there's a much higher probability, like I said, of, you can mess up in a lot of ways, and you would have a larger entropy. So related to that is what's sometimes referred to as the Boltzmann equation here. And in the Boltzmann equation, this is it right here. S is the entropy. K is the Boltzmann constant, which is the guy on the bottom there. Natural log of W, and W is the number of microstates. So sometimes when people talk about sort of probability, they talk about microstates. And microstates, if you want to think about it, is really just how many different ways you can sort of accomplish something. So when we look at this, and these could be circles and boxes, this could be, a carnival game, right? So let's say we were at a carnival and, you wanted to win, the big stuffed animal there, giant stuffed animal. And to do that, you gotta get all 4 balls on one side only, right? And so there's really only one way you could do that. Technically, there's 2. You could do it on the right or the left, but we'll just call it 1 for this. Now, let's just say, all right, if you want like the medium-sized prize, you need to get at least 3 balls on one side and 1 on the other. And there are 4 different ways that you can basically accomplish that. And hey, you want the constellation stuffed animal, you just need to get 2 on each side. And there are 6 different ways of doing that. So clearly, most could probably get the 2 on both sides if the carnival is not rigged or anything like that the balls just bounce out or something like that. But there's a much higher probability, right, of you getting two per side than there is. Got to get them all on one side in this particular case. So we could see that just by going into this equation. For example, if we did the top one there, and there's only one way, natural log of 1 is 0, right? So we have a really small entropy value in this case, as opposed to here where there are multiple ways and a higher probability of occurring. When you do the natural log of 6, that's like 1.79. So again, a much more positive value for entropy in this case, again, because there is multiple ways to do that. So again, more multiple ways of achieving something will result in a higher entropy value, as opposed to if there's only one or a few ways of accomplishing something, you would have a much lower entropy value. Any questions on that there? So these are all processes here that do lead to an increase in the entropy. And we would all have positive entropy values here. And again, we're going from a more ordered state to more disorder, more ordered versus disorder. And actually the making here of a solution, which is made up of a solute, which is the stuff you dissolve in it, and the solvent, which is the stuff you dissolve the solute in, is actually an increase in entropy for both things. So for example, if you took an ionic compound before you dissolved it, it is very, very ordered, right? It's in a three-dimensional sort of really, really ordered event with all the positive and negative ions kind of glued together in a very ordered, repeatable sort of pattern. Also, for example, if you took something like water, which is like a solvent, before you do anything with water, it is also quite ordered, as all the water molecules are hydrogen bonded to each other, and they're very, very ordered. So in order for this thing to dissolve, you got to break apart some of these bonds, you got to rip apart some of that, and now you got everybody jumbled together over here. And obviously that's a lot more disorder that's happening, a lot more craziness and things moving around than it was when we began. So in the process of dissolving or making a solution, you're actually increasing the entropy for both the solute and the solvent. Temperature also is a factor that can definitely increase the entropy. If you end up with a higher temperature, you would expect things to move faster and have a lot more energy, right? So like you light a fire under somebody, they move quicker, right? So same idea here. If you increase the temperature, things have a lot more energy, which means they're going to be moving around a lot more, and it's going to cause a lot more sort of craziness, and that's going to increase the uh, disorder and give you a more positive entropy. The opposite would be true if you obviously lowered the temperature, right? So if you lower the temperature, everybody's going to lose energy and kind of slow down and not move around as fast, right? So it's going to create a lot more order than there was when things were moving out really fast because they have a lot of energy. So take a moment for each of these and decide, does the entropy of the system change for each of the following processes? Does it become more positive? Does it become more negative in each of these cases? Now in the liquid state, a lot less energy. So you are increasing the order, you're decreasing the disorder. So our delta S here should end up being negative in this case as the entropy is decreasing here. Down. The forming of a sucrose crystal from a supersaturated solution. So a crystal is a solid and a fairly organized solid. So that also is going to increase the order in this case. So the delta S here is going to be negative. And again, our entropy is basically decreasing in this particular case. If we heat hydrogen gas from 60 degrees to 80 degrees, we're increasing the temperature in this case, so gas molecules are going to start flying around a lot faster, and that is going to increase the disorder, and we would expect our entropy to be more positive in this particular case. And lastly, sublimation. Sublimation is the process of going from solid directly to gas, skipping the liquid cleanup, right? And obviously we're going from something that's in the solid state to things flying around basically. And that definitely would increase the entropy, and the delta S here would be more positive. Any questions on any of those there? So let's talk about entropy here. As I mentioned before, entropy really is a state function along with enthalpy and some other things, energy, pressure, and volume. And again, state functions, as a reminder, as I mentioned, doesn't really determine on the path. It's really two things that are important: where you start and where you end. And for potential energy, for example, these two guys, the blue guy took the more direct route up the hill. The red guy took the scenic route and wrapped around the hill. But in terms of their potential energy, they both basically have the same potential energy because they both began and ended at the same place. And that's why a lot of times we will do like the change in something as like final minus initial state. So a lot of times when we take the change of something, we do final minus the initial. And in a reaction, when we think about a reaction, we have our reactants that go to our products. So a lot of times with thermodynamic type properties, we find the change in whatever it is by taking the difference between the products minus the reactants, as the products is really our final state and the reactants is our initial state, right? So that's why a lot of these sort of thermodynamic sort of calculations, you add up everything on the product side and subtract it from everything on the reactant side. Like you do, for example, one way of calculating delta H, right? You go to a table, add up all the delta H values for your products, minus it from the delta H values from your reactants, and that will give you the delta H for the reaction. So that's why we do a lot of those things. Now, this is a table from your book there of some delta S values. And delta S values, one of the things that are slightly different than, say, like a delta H value that you may find in a table, delta S values are all positive. So they're all positive type values. The other difference is actually the units, and units are really important here. And the units of some very common thermodynamic sort of values that we'll come across is, for delta S, typically the units are in joules. And typically speaking, delta H is typically in kilojoules. And there will be some formulas where we'll use both of these guys together. And it's really important that you do that conversion of the units. Otherwise, you're going to be off by a factor of 1,000. So those are some common issues that sometimes students have when they're doing calculations. They kind of forget one's in kilojoules and one's in joules, and they're off with their calculation again because you're like 1,000-fold difference there. Um, the other difference that you may notice is, as you may know, or if you don't know, let me tell you, the delta H value or delta H of formation, which are the table values that you look up in a book, for things in their natural sort of standard state are 0. Yeah, so things like H2, N2, O2, if you look them up in a delta H table, you basically have values of 0. Different than that, though, here for S's is we actually do have, as you can see there, values for things like that. So you will find some entropy values for things that we normally find as zeros when we're doing delta H. So that's a little bit different as well. So let's talk about some of the first laws of thermodynamics and the second law of thermodynamics. The first law of thermodynamics, again, is pretty much what you covered there in Chem 50, which is all about the energy. So that's your delta H. That is your law of conservation of energy. Energy, again, as we talked about, cannot be converted, cannot be created nor destroyed, but can be converted from one form to the next. The second law of thermodynamics is what we're talking about right now, which is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So when we look at entropy to help us determine whether or not have a spontaneous process, we actually have to calculate the delta S of the universe. And the delta S of the universe is made up of two things: the delta S of the system and the delta S of the surroundings. Now, a reminder that when we talk about sort of thermodynamics, there's two things that we oftentimes talk about, which is the system. And the system is pretty much whatever you're interested in. So, for example, a lot of times our system is really the delta S of the reaction, right? We're interested in the reaction that's taking place. Your system could be like your beaker, your flask, your test tube, whatever it may be. And then we basically have the surroundings, which is everything else, right? So that is everything outside of that. So if you were doing a reaction in a beaker, your beaker would be your system, and then everything outside of that beaker would be the surroundings, right? And a lot of times, especially for example, with energy, we look at the flow, for example, of energy, say to the surroundings from the system, or from the surroundings to the system, or the system to the surroundings. So we look at that flow of energy from one place to the next. And that was what I was talking about earlier, that sometimes helps with spontaneous sort of reactions, is that kind of flow of energy, or the spreading out of energy is sometimes very helpful. Here we're also looking at, as we'll be talking about, sort of the difference in the entropy, or the amount of disorder as you go from the system to the surroundings. So we do use the delta S of the universe to help us calculate whether or not a reaction is spontaneous. And if you do that and you hit a positive value for the delta H of the, I'm sorry, delta S of the universe, that is a spontaneous process. By default, if you hit a negative number, then the reaction would be non-spontaneous. If you hit is equal to 0, then the actual reaction is at equilibrium. At an equilibrium process, as you know, right, the rate of the forward reaction equals the rate of the reverse reaction. And what it does, as we talked about, is it pretty much locks everybody into place, which means if you're at equilibrium, there's really not much change happening, right? Because nothing's really changing at that point. There's no like sudden influx of heat or energy happening. There's no movement of matter happening, because as soon as you go one way, the other way goes back, and the thing stays at equilibrium. So if we do have that at equilibrium. Now, we will talk about for each of these how we calculate the delta S of the system versus the surroundings. So let's start with that so we know how to get to the universe. So we're going to start with the delta S of the system. And the way that we calculate that are the delta S of the reaction, which again, as I mentioned, is sometimes what you're interested in. We calculate really by just taking our products minus our reactants. So this is a thermodynamic table like we saw on the previous slide. You would go there and you basically would take all the delta S of your products, and you would subtract it from all the delta S's of your reactants. Just like you do with delta H, with delta S, you also do need to take the coefficients into account when you do that. So, let's just say that we had 2a plus 3b goes to 4c. And let's say in our delta S table here, A, B, and C, A is 495 joules and 262 joules, and clearly making up numbers, 136 joules here. And if we found these values, obviously, in our table, we would do our delta S for this reaction here by taking our products, and we do have to take the 4 and multiply it by the value we would find in the table, 136 joules. We then would subtract it from our reactant. So we have 2 times A's value from the table, 495 joules. We would then add it to 3 times the value we have here in the table for B, 262 joules. And for fun, let's see how I did making up numbers here. Let's see what we end up with. We got 4 times 136 minus 2 times 495 plus 3 times 262. And we're going to end up with minus 1232 joules in this particular case. That would mean that this situation, we are increasing or decreasing the disorder. We're decreasing the disorder. We're increasing the order, right? Because we have a negative value for delta S. I actually made up the numbers pretty right there, so that worked out actually pretty good. So that's what we end up with in this particular case. So let's take a look at this one here. So why don't you calculate it? And I feel like I'm missing a number there. I am. What we got there? CO2, I think. I think it's on that slide. Let's see. Do I have that? I do, I think. CO2, yeah. 213.8 we'll use. 213.8 joules per Kelvin per mole is the S of CO2. All right, so these would be the values you find in the table. So calculate the delta. So obviously, if they were not provided for you, you'd have to go look it up in a table. And we're going to basically do our products minus our reactants. So our delta S in this case, going to be on our product side, we have 2 times our CO2 value of 213.8 joules per Kelvin per mole. That's going to take care of all of our products. I'm going to go underneath so I don't run out of room. Then we're going to go to our reactants, 2 times our CO, 197.9. We're going to add it to our other reactant, which is O2, and that's basically 1 times our O2 value there, 205. And that is going to get us here. Looks like negative 173.2 joules in this case. Stop any questions on the calculation. The amount of disorder is increasing or decreasing in this case? It is decreasing in this case. Now, we can actually, in this particular case, make a fairly good prediction as to what the sign of delta S should be in this particular case. And that is from looking at the actual equation. And in this reaction, we have 2 gas molecules there. We have 1 gas molecule there. That's a grand total of 3 gas molecules on our reactant side. On our product side, we're actually ending with 2 gas molecules. So in this particular case, when we look at the reaction, we have 3 things starting to flying around, and then we end up with only 2 things kind of flying around in your face. And that means we have created a lot more order in this case, right? So we have less things kind of flying around. That's going to create a lot more order. And we would predict in this case that the delta S of this reaction would be negative, which is what we just got. And that's a good thing to think about because you can't make that prediction before you do the calculation. Just make sure you didn't screw up the calculation. Here, if you got a positive value, it would not make sense based on what you're seeing in the equation. So if you look at a reaction and you do produce more gas molecules than you started with, then you would expect a lot more disorder because there's a lot more crazy things flying around, right? And you would expect the delta S to become more positive. If you create less gas molecules like we just did here, you would expect it to be more negative as it's creating more order in this particular case. First off, any questions on that there? Does this value tell us if this reaction is spontaneous or non-spontaneous? The answer is no, it doesn't, because we need to calculate the delta S of the universe to make that decision. What this will basically tell us is, in terms of the reaction, are we increasing or decreasing the order or disorder, however you want to think about it? That is what this value will tell us. It will not tell us if this reaction is going to be spontaneous or non-spontaneous. Any questions so far? So as I just mentioned a second ago, you can make a fairly good prediction as to what the sign of delta S should be based on, gas molecules more or less being formed. If you actually do end up with sort of the same number of gas molecules on each side, then it's sort of a hard decision. It could be positive, it could be negative, but you probably will have a relatively small value for delta S in that particular case. So for example, here, without doing a calculation here, would we expect this reaction to have a positive or negative delta S value for the reaction? Yeah, it would be negative in this case. Again, this is a solid. That is a gas molecule, so that's 1. And on this side, this is actually a solid, so we have no gas molecules. So we're going from a system of 1 gas molecule flying around to a system of no gas molecules flying around. That definitely is going to increase the order, and we would expect our delta S in this reaction to be, for this reaction, to be negative. Any questions on that one there? There is a lot of questions, as we will see as we go through this chapter, and you'll see when you do some of the homework problems, is There's a lot of questions in thermodynamic chapters where they really don't give you values or numbers, but they go like, hey, this is positive, this is negative. Do you expect this to be spontaneous or non-spontaneous? So there's a lot of those type of questions in this chapter. Now, we talked about how to calculate the delta S of the reaction or the system. So the other thing that we need to calculate to help us get to the delta S of the universe is the delta S of the surroundings. And the delta S of the surroundings does sort of determine or is sort of based on the entropy of the reaction, or the enthalpy of the reaction, delta H of the reaction. So here on the left, we have an exothermic process, which means our delta H here is going to be negative. That is going to release the energy from the system to the surroundings. The result of that is when we think about the surroundings are going to pick up a lot of heat and energy. And that's going to cause everybody in the surroundings to kind of move around crazily, right? Because they picked up a lot of energy. They're going to have a lot more energy. And that, in terms of the surroundings, is going to actually increase the entropy of the surroundings. So for our surroundings, we would expect the delta S of the surroundings to actually be a positive number in that particular case, because it's gaining all that energy. It's going to cause a lot more craziness to occur. Opposite over here on our endothermic process, our delta H in this case would be a positive number, as it's going to absorb energy. The result of that is the surroundings is going to give up its energy to the system. And because of that, the surroundings are now going to lose a lot of energy. So if you just want to think about surroundings as like gas molecules, they would now be flying around, dramatically drawn here, a lot slower, right? They're going to be moving a lot slower, a lot more order basically happening. And that's going to cause the surroundings to become more ordered because it has less energy. And we would expect for the surroundings in this situation to be a more negative value. Now, there is sort of a relationship between those two things. And the relationship is the delta S of the surroundings is proportional to the minus delta H of the system. So what does that mean? It means what we just sort of talked about. If I have my delta H of my reaction, and that is going to basically be our delta S of our surroundings, the relationship there is kind of an opposite relationship. So, for example, actually, I'll put the negative over here to get to our positive here. So, if our reaction is exothermic, our delta H would be negative, and a negative will actually turn our delta S of our surroundings into a positive. And if our reaction is endothermic, our delta H would be positive, and negative of a positive would turn our delta S of our surroundings into a negative value. Now, there is a sort of asterisk to this, which is, for example, if we had a exothermic reaction and the surrounding temperature to begin with was a really high temperature, would the added amount of energy coming from the reaction make that big of a difference in terms of the entropy? And the answer is no, it probably won't. So just to illustrate that in a bad example, if you just lit a match in a regular room like this, you could feel the heat and energy, right, coming off of the match, right? And you could feel that exothermic reaction occurring. If you took that same match and you lit it and you put it in an oven that's at, don't try this at home, by the way, if you put it in an oven that's like at 550 degrees, right? That little match and the energy coming off of that match versus the room temperature of like 550 is not going to make a big difference, right? In that case, right? So the surrounding temperature makes a big difference in terms of whether or not you'll see a big change in the entropy. If you have a really high value to begin with for temperature, you won't see probably a very big entropy change. Opposite of that, if you have a really low temperature, you would probably see a pretty good entropy change of the surroundings. So how do we actually calculate the entropy of the surroundings? And it is this formula here, which is totally messed up here. So let me just rewrite it here. I'll go up on top. delta S of the surroundings is equal to our negative delta H of the system or the reaction divided by our temperature in Kelvin. Yeah, so it does need to be in Kelvin here. And as I mentioned before, if the temperature of the surroundings is high, the increase in entropy will be small. But if you have a lower temperature of the surroundings and you have an exothermic reaction, you will see a much larger change. So this is how we calculate our delta S of the surroundings. We calculate our delta S of our system, as we talked about, by taking the delta S of our products minus the delta S of our reactants. You basically add both of those together, and that is going to get you your delta S of your universe, which you can use to determine if this reaction is going to be spontaneous or not. Any questions on that there? All right, so why don't you try one then, and let's see. Calculate the delta S of the system, the delta S of the surroundings, and determine whether or not this reaction of ammonia or the formation of ammonia is going to be spontaneous at 25 degrees Celsius. Look, so in this case, we do need to calculate delta S of the universe to make that decision if it is spontaneous or not. So we need our system and we need our surroundings, and then we can add them together. So it doesn't really matter which one you start with. I can go system first here. So again, we're going to do our basically products here. Products minus our delta S of our reactants. So putting that in on our product side, we have 2 times our NH3 value from the table, which is obviously where you would go find it if it was not provided. We're going to subtract it from our reactants. So we have 1 nitrogen, 192. Going to add it to 3 times our hydrogen, which is 131 in this case here. And that is going to get us here. It looks like, let's see here, 193 minus 192 plus 3 times 131. We'll go with a negative 199 joules here, basically, in this case. And that's the delta S of the system. And that does make sense if we just look at the reaction, right? Again, this is not telling us if it's spontaneous or not. But on our reaction here, we have 4 gas molecules, right? And we're ending with 2. So again, we're going from a system that has a lot more disordered things flying around to a lot less things flying around, a lot more order in this case. So we would expect for our reaction, our delta S here to be negative, which it is. Now for our surroundings, which is the other sort of component we need to figure out our universe, our delta S of our surroundings is going to equal negative delta H of the reaction divided by our temperature in Kelvin. So a plus 273 to that guy, going to give us 298 Kelvin. And in this case, we'll plug in our delta H, which was given to us. So this is a negative and a negative, right? So we got double negative there. That's going to be a 92.6. I am actually going to multiply it by 1,000. And again, I'm doing that to get it into joules because frankly, that's in joules. So might as well get them both into the same units divided by 298. If you didn't do that, then you will obviously have my answer just 3 decimal places over. You got 92.6 times 1,000 divided by 298. We'll call it 311 joules in this case. And that would be our delta S of our surroundings. This also makes sense if we think about it. We're at 25 degrees, which is like normal temperature. This reaction is exothermic, right? It's going to release the energy to the surroundings. The surroundings will pick up that energy and go crazy, and it should cause it to increase the disorder in the surroundings. And again, we see a positive value for our delta S of their surroundings. So again, all these things should sort of make sense. Lastly, here to calculate our delta S of our universe, we just need to add them together in this case. So we got negative 199 plus 311. And again, this is the reason I got everybody into the same units. You do not want to be adding, which is a common mistake people do here, kilojoules and joules together at this point. And that's a very common error people make. Minus 199 plus 311 going to give us a 112 joules. That means that the delta S of the universe is positive, and this reaction is spontaneous. Yeah, so this reaction should occur under these conditions because our delta S of our universe is positive. This is also a really good example of a reaction that's spontaneous that will take forever if you don't use a catalyst. So although this reaction will occur, it's a very, very slow reaction, and but it will happen spontaneously without any type of intervention by anything else. Any questions on any part of that calculation, system, surroundings, universe? Then let's talk about the third law of thermodynamics. And the third law of thermodynamics is a perfect crystalline substance is zero at absolute 0 Kelvin. So obviously, if you have a perfect crystal, basically, there's kind of only one way to achieve that, right? Perfection. And that would mean that your microstate would be 1, right? There's only one way to kind of do that. And as we saw earlier, if you put the 1 into here, that's going to zero this out, and it will give you an entropy of 0 for that. We do have the increase in entropy, as we talked about, going from solid to liquid to gas in this case. And we also have entropy that occurs as we do phase changes, right? So as we go from solid to liquid, or liquid back to solid, we have sometimes what is referred to as the delta S of fusion. And as you may remember from Chem 50, there is a certain amount of energy required to do that transition, going from solid to liquid or liquid to solid. That is the delta H of fusion, right? And for water, the delta H of fusion is like 6.02 kilojoules per mole, or roughly 335 joules per gram, give or take a joule there. And that is the amount of energy, as you may remember, occurs or is needed when we change the substance at its normal melting point and freezing point, not change the temperature or anything like that, but simply take, for example, ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. That is the plateau version there that's happening. We don't change the temperature, but we do change the phase. It is a endothermic process, right? As you go from solid to liquid, you have to put energy in to do that. That is a positive, so we'll go with the 335 number, joules per gram. And it's a exothermic process as you go from liquid to solid. You have to release that energy. Everybody will slow down because they lost the energy, and they basically will come together in a solid. That's a negative 335 joules per gram, or obviously a positive or negative for our 6.02 kilojoules, if you want to use it per mole. Now, when we think about the delta S of fusion, as we go from solid to liquid, we're increasing the amount of disorder, and we should end up with a positive value for the delta S of fusion. And if we're going from liquid to solid, we would actually end up with a negative value for our delta S of fusion in this particular case. We have the same sort of transition that occurs between go from liquid to gas or gas to liquid. That happens at the normal boiling point, right, of a substance. This happens at the normal melting point, freezing point, basically. And there is the delta S of vaporization. And again, that is the transition as we go from liquid to gas or gas to liquid. And much like what we have over here, there's also a energy component to that, which is the delta H of vaporization. And delta H of vaporization for water, for example, is roughly 40.6 kilojoules per mole, or about 2260 joules per gram. And it's the same idea. We are, again, not changing the temperature at this point. We're just simply, for example, with water at 100 degrees Celsius, taking liquid water at 100 degrees Celsius to basically steam at 100 degrees Celsius. no change in temperature. And again, that's happening right here. And we see a flat line. And again, that's because the temperature is not changing. Same idea. It's an endothermic process going liquid to solid or liquid to gas, 2260 joules per gram positive, negative 2260 joules per gram. Again, here we would still have our positive going in this direction and our negative heading in that direction. Any questions on any of that there? And we'll talk a little bit more about this later on as well when we get to some of the transitions. Now, who wants to always calculate the delta S of the universe to try to determine whether or not a reaction is spontaneous, when in most cases we're really just interested in what is going on in our reaction? And we can actually use another thermodynamic value, which is Gibbs free energy, and that is delta G. Delta G is the change in Gibbs free energy. Gibbs free energy, much like the name implies, is energy that is free to do some type of work. So it is available to do some type of work on something, or work being done on it. And as we just talked about, in a spontaneous process, the delta S of the universe will be positive. In an equilibrium process, it will be 0. This is one of 5 different ways we will see delta G calculated in this chapter. Maybe it's 4. But this is one version of how we could get to a delta G. And the delta G in this case is equal to the delta H minus T delta S. So this is our Gibbs free energy. This is our enthalpy. T is our temperature that has to be in Kelvin. And S is our entropy. So this has pretty much all 3 thermodynamic values together here in one equation or one formula. And you do definitely want to be really careful about units here, as we were talking about earlier. Delta H is, again, typically in kilojoules. Delta S is in, not S, but joules there, in joules. So once again, you do need to do a conversion. You could either convert them both to kilojoules or convert them both to joules, whichever way you want to do it. But you typically do need to do a conversion here. I will say in most cases, delta G is given in kilojoules. So usually the ending sort of value for delta G is usually given in kilojoules. Now, we could use Gibbs free energy here to help us determine whether or not a reaction is going to be spontaneous by the sign. And if you calculate the delta G and you end up with a negative value for delta G, then the reaction is spontaneous the way it's written in the forward direction. That again means that we would expect this reaction to occur without any type of intervention. It would occur going from reactants to products as it is written on the page, and we would expect that reaction to again happen. Once again, as a reminder, being spontaneous doesn't mean it happens fast or slow. It just means it's going to happen. So that's all it will tell you in this case. If you calculate delta G and it is positive, put that around, the reaction as it is written is actually non-spontaneous, which means that reaction will not occur the way it is written without any type of intervention. But sometimes confusing, it is referred to as the reaction will be spontaneous if in the reverse direction. So if you flip the reaction around and do it in the opposite direction, the reaction would then become spontaneous. The reason for that is if you flip the reaction, your reactants become your products become your reactants. You actually end up with the same value. The only thing that changes is the sign. It goes from, for example, positive to negative in that case. And if delta G is equal to 0, it will be at equilibrium. Now, when we talk about these delta G reactions, the best piece of advice is you should choose the delta G formula that fits the information given to you. So, for example, if you're given like an H and an S value, this would probably be the winning one to do. If you're not given an H and S value, then you probably would use some of the other delta G value formulas that we will see. For example, if you're not given H and S, but you are just given an actual reaction or equation, you could calculate the delta G of the reaction. And the delta G is calculated pretty much like delta H and delta S in this case. If you are only given a reaction or an equation, delta G will be just like everybody else, delta G of the products minus the delta G of the reactants. And again, just like we did previously, you do need to take the coefficients into account and multiply them by the values you would find in the table. So you would go to the table, and by the way, when you go to the table, they are sometimes referred to as the standard free energy of formation, the delta G of F. Just like when you go to the table, delta H of F is sometimes what it's referred to. Now, you may be wondering again what the little naught means up on top of these things, like delta G naught, delta S naught. This little naught here means essentially that things are under standard conditions. Let me see that little kind of knot on one of those values. What does that mean? For the most part, what that means is it's usually considered sort of table conditions, like you look it up in the table. And what that really means, though, is what we see in the table. If it's a gas, then all the pressures need to be 1 atmosphere or 1 bar. If you're dealing with some type of solution, the concentration needs to be 1 molar. Sometimes people will also throw in there 25 degrees Celsius, but really these are the two things that make something sort of standard conditions. If the pressures are not all under 1 atmosphere, or if it's not all 1 molar, if you're dealing with concentration, then you're not under standard conditions. But most thermodynamic tables, which you could find in your book, and usually when you go to that table, they have a delta H, a delta S, and a delta G sort of column. Most of the time when you go to that table, these are the 3 conditions that you typically will see when you look up those values from a table. So here we could actually just calculate straight up the delta G, and if it's positive or negative, it will tell us if this reaction is spontaneous or non-spontaneous by just a delta G value. Delta G, as I mentioned before, is typically in kilojoules. It is also similar to what we see with delta H, which is when you go to a table for delta G and you're looking up something like O2, N2, you're going to hit some zeros for delta G, basically, in those tables. So anything that's standard state for delta G is typically a 0 value as well. So why don't you try one? Here's some of the values there on the bottom. O2 is 0 kilojoules. So calculate the delta G for this reaction and determine is it spontaneous. Okay, so let's take a look. So obviously, once again, you would go look this up in a table if it wasn't provided for you. We're going to do basically our products minus our reactants here. So starting on our product side, we have 12 CO2s. Each one is negative 394.4 kilojoules plus 6 times our water. A reminder as well that you do want to make sure that when you do go to those tables that you do find what you're looking for, and you also want to make sure you do find it in the correct state. So sometimes things are in different states, they'll have different values, so make sure you do look up the right state, not just what you're looking for. We'll times it by our benzene here, which is 124.5 kilojoules and 15 times 0 basically in this case. That's going to get us here, looks like negative 6405 kilojoules in this case. First off, any questions on the calculation? This reaction is spontaneous or not spontaneous? Reaction is spontaneous, yeah. Reaction is spontaneous because we have a negative delta G. We would expect this reaction to proceed in this direction towards our products, right? So our products are thermodynamically favored here. So reaction should head that way. Any questions on that there? All right, we're laid up there for today.